So the toric code is a physical realization of the quantum lattice Z2 gauge theory. So the construction is the following. We have our square lattice with spins 1/2 on the bonds. And we are in the total Hilbert space, so which I will just call H, that is C2 tensor 2L square, because we have this many spins. And we have defined two operators that now I will call A and B. So the A operator is based on sites labeled by N. It involves the 4 spins that come out, and you apply X. And the B operator is based on plaquettes labeled by P. And on these spins, we operate with Z. So let me write the formal definition. AN is the product on the spins coming out from N of sigma X. And BP, the product of the spins around the plaquette of sigma Z. Okay. And we have seen that these operators commute. And our Hamiltonian of the toric code is defined by minus this stuff. And we have seen that at low energy, so we can put ourselves in the limit where U is much greater than J. And L low is the subspace of the psi such that the expectation value of the energy in this state is much smaller than U. We've seen that this subspace is the same of the gauge theory. In particular, the ground state is exactly the same. So the ground state is 2 to the 2G degenerate. Where this 2G comes from, because for every hole, so G is the number of holes in our lattice, there are 2 copies of a spin 1/2 algebra that are these operators here. So W1, Z, and W1X, and the same thing for the other direction, namely W2Z, W2X. And these operators, so WXI, WZI, anti-commute, and they all square to the identity. So they realize the spin 1/2 algebra, but also they commute with the Hamiltonian. Commute. Which means that if I act on a state that is in the ground state subspace, then I stay there, right? Because it commutes with the Hamiltonian, I cannot change the energy. But there is a difference between these operators and these operators, because so if psi belongs to the ground state manifold, which is, we saw the span of 4 states, one that we call 0, and then W1x0, W2x0, and W1, W2, XX0. So if psi belongs to the ground state, AN psi, basically by definition, because our ground state is defined as those such that these operators have eigenvalue 1 is equal psi, and BP psi is equal psi. So they do nothing on the ground state. Whereas, as you can check directly, these operators on the ground state do something different. No, you change state. They're non-trivial. They realize an algebra. It's exactly the algebra that makes you move inside this subspace. So what are the eigenstates? So this Hamiltonian is completely solvable because it's just the sum of commuting operators. So what are the eigenstates? Oh, well, in these quantum numbers, the Hamiltonian is already diagonal. Can you see? So the eigenstates let me label them by these two numbers, are given by this set of states So each of these quantum numbers has eigenvalues +1 and -1. The ground state is the one where all the A and all the B are +1. And then you are left with a choice of 4 states here, from which the degeneracy comes. Then the excited states are, so I will say that every time, what is this number, NV and NP? So NV is the number of AIs with eigenvalue -1. Let me use C, sorry. C stands for charges. And this NV stands for vortices. So I will just call charges the excitations of the A operators, and vortices the excitations of the B operators. So definitely the ground state is such that, so psi in the ground state, psi 0, belonging in the ground state, has this form. It's all +1. And then whatever. So in this notation, it has the energy of 0, 0. And there are 4 ways of doing it, right? Because then I can change these quantum numbers without changing the energy. So what is E0? Well, it's obviously minus L square U minus L square J. So what are the excited states? Okay, so the first excited state, I need to excite these guys, right? Because J is much smaller than U. And I can only, all these excitations come in an even number. So NC and V are even numbers because the product of all the N and the product of all the BPs, as we have seen many times, is the identity. So the energy of the first excited state will be equal to, okay. So now the smallest thing I can do is to excite 2 of these plaquettes. Okay? So this means that here I have minus L square U, but now it's minus L square minus 2 J. And now these 2 plaquettes get an energy 2J. So you can see that this is equal to is 0 plus 4j. And so on and so forth, right? Then you, what is the degeneracy of this state? So this one is for degenerate. And this one, what is the degeneracy of the first excited state? So how many states there are with this energy? Yeah, so the first one, the first BP, I can choose it in L square ways. The second in L square minus 1. The order doesn't matter, so it's over 2. Are we done? Times 4, right? Because I can still do it in 4 different ways. And so on and so forth, right? So if you do the very simple exercise of computing all the degeneracies and you sum all of them, you will find an exponential, which is 2 to the 2L square. Okay. So this is the spectrum. Okay. Now we want to see, so this is called the toric code Hamiltonian. And we are interested in studying the Hamiltonian of the toric code in the presence of a local perturbation. So remember when we did the gauge theory, we treated as a perturbation the external field in the x direction that was gauge invariant. But now we are beyond gauge theory. So this is any local operator, doesn't need to obey the gauge constraint. Yeah?
I think previously we discussed that the number of the quantum number is 2L squared. Yeah, the quantum number. And now we have 2L squared plus 2.
Well, but you see this? Yeah, so no. Only L squared minus 1 of them are independent. Once you have fixed a configuration of A1, so you fix what is the value of A1. You fix what is the value up to L squared minus 1. The last one is determined. Okay? So to label the states, you only need these ones. Okay? So the last one is automatically determined. I might not write it. The reason why I'm writing it is because when you compute the energy, you must also, in the Hamiltonian, there is also that quantum number. The fact that it's determined by the others doesn't mean that it's not there. So there are L squared minus 1 of A, L squared minus 1 of B, then W1 and W2, total 2L squared. So all the counting is all right. So we are interested in this. To understand this, it's very interesting to see the toric code as a string theory. So what do I mean by this? Okay, so we have already introduced our string operators in this way. So here I have a W alpha of gamma. Alpha has 2 values, is X or Z. And gamma is a curve on the lattice or on the dual lattice. What I mean is that, as you can see, these yellow strings that carry Z, by convention, I always draw them on the links. And the green curves that carry X, I always draw them through the plaquettes. Okay, so on the dual lattice. Okay, and what is this? Is the product of sigma alpha L on all the links that belong to the curve. By belonging here, I mean that either are on the curve or are crossed by the curve, depending whether we are using the X or Z. Okay, so this is a string operator. So we have three possibilities for these string operators. Is that gamma is closed and contractible. In this case, W alpha, so I call it C, this contour. Well, it's such that this is, so it's either the product, so for when this is X, this is the product of the n inside the contour. So I have a contour, and there is an area A here. So let me call this area A of C. So it's the product of all the AN inside this. Because you remember, we saw it. When we do a product of many A's inside a closed contractible curve, all the interior links are annihilated and only sigma x on the boundary survive. So we can write it like this. And similarly, for all the plaquette inside the area, this is BP. So this is for alpha equal x. This is for alpha equal z. Okay, second possibility. Gamma is closed, but not contractible. Then our W operators are just what we called W1 and 2 with X or Z. These operators appear. Third possibility, gamma is open. So it has endpoints. And I will say gamma has endpoints I and j. So let's see what an open string does. What does an open string? So this operator, W gamma, let's say W gamma x. So this is I, and this is j. Let's apply it on our ground state, side 0. Well, so let me show you a picture. So let me make it straight, just for the sake of simplicity. You see all the star operators that are inside the curve. So, sorry, let me, Z. So here I have Z, 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 Z. Okay. Well, you see, this star operator is flipped twice. This star operator is flipped twice. This star operator is flipped twice. So all these don't change their eigenvalue. If they're +1, there will be again +1. The string operator commutes with this, in other words. But it does not commute with this. Because this string with respect to this operator is like having x1, x2, x3, x4, z4. Right? So these two operators anti-commute. So the result of this is that we get this state where all the AN are equal +1 and all the BPs are equal +1, but for AI will be equal to -1 and AJ will be equal to -1. Do you see that? Do you see that? So an open string operator will commute with all stars operator, but the ones at the endpoints, which will anti-commute, so it will change the eigenvalue from +1 to -1. Therefore, we get an excited state. So excited states are open string states. This is what we, by what we mean is this, that we can write them like this. If I want to have a state with 4 excitation, then I will have W, say, Z, ij, gamma of gamma ij, times WZ, gamma mn. And in this way, I've created A excitations at I, J, M, and N. Notice that another string with the same 2 endpoints would have exactly the same effect, right? I would not change all these stars, but only the 2 at the endpoints. So the strings in themselves are invisible. What counts is their endpoints. So they are isotopic, we say. Okay. So what excited states are open isotopic string states. At the same time, let me get a closed string, a WC of alpha on the ground state. A closed contractible string. But the closed contractible string is, say, for instance, in the case of alpha equal x is equal to the product of these operators. Right? And each of them on psi gives me psi. So also the product of them gives me, again, psi 0. So you see, these operators do nothing on the ground state. So in the end, these operators do nothing on the ground state. These move me inside the ground state manifold. So I get to an orthogonal state. And this gets me above the ground state. So in this way, we realize the full algebra in the whole Hilbert space of these excitations. Now it would be nice to see all these. Yeah.
When you explain the open string, like you said, the star operator is not like everything in interior is part cancelled and
Yeah.
survives. But
Yeah.
in case of endpoint, like this part, the one of the legs overlapping with other stars inside is also cancelled, isn't it? So is that exactly equivalent to the star operator acting on the endpoint? Is my question clear?
I'm not sure I understand. Are you saying this, that if I have this string, then there is also this string that does the same thing? This is what you're saying?
No.
No, okay.
Let me ask you later.
Okay. So it would be nice to complete the string picture by using what we learned about the ground state in the gauge theory. Remember that we say that this state that we call 0, this one, is equal, with some normalization, to the product of 1 plus an over the state with all spins up. As you can see, this state is in fact in the ground state, namely to obeys all those constraints, an psi equal psi, bn, bp psi equal psi, why? So the state all spins up already obeys all of them. It's a good reference state. BP is made of just sigma z operators. So on all the state all spins up does nothing. And now I'm projecting, this is the projector onto all those constraints. There is a 2 missing, but it's taken care by the normalization anyway. And we saw that this is equal, because this is the last thing we said, to this guy. It's equal to the identity. So here we have a normalization, plus the sum over all the possible star operators, plus the sum over all the possible pairs, and so on and so forth, on this reference state. We call this state the vacuum of strings. Well, now you see what is doing this thing. This is a huge superposition. Right? Let's look at this superposition in the string picture. So we have the vacuum, the identity. So we have 1 over n. We have the vacuum of strings, no strings, plus, what is an? Well, it's flipping these 4 spins. So this is like applying the X operator on this small loop on above this reference state. So this no strings plus the sum of small strings. What is the one with the 2? Sorry, here, 2 of them. Well, it is either 2 of these guys, or a bigger one, right? Because if they are contiguous, the 2 star operators, this one cancels, and we have a bigger string. So we have this thing, and so on and so forth. But, by the way, what are these? This is the sum over all the possible products of A's. Okay? Do you see it? These are all the possible products of A operators. So if I have a set and I make all the possible products, what is this called? The set of all the possible products of elements that are in another set. This is the associative group. So let me call it G. Is the set. This is the notation. Is the set of all possible products of A's. So this thing is 1 over n, the sum over the elements of this set, acting on the reference state, which by definition I will call ket G. And of course, what is this normalization? It's the square root of the number of elements in this group. And what is the number of elements in this group? Well, this is usually in group theory, this is a very hard task, but this time it's easy because these operators have a very simple group algebra because A squared is 1. So, and they're not all independent. So how many there are, we already know. 2 to the L squared minus 1. So this is this number here. So you see that the ground state that we call the 0 is the equal superposition of all the closed string, closed contractible string states with equal amplitude. It's the equal superposition. It's very important. So there are a lot of fluctuations. Basically, you don't know in which of these closed string states you are. It's fluctuating between all of them with equal amplitude. And the other states, W1, W2, W1, W2, are just the same state on top of which I act with one of these non-contractible string operators. Now you can see that the fact that WC on psi 0 is equal to psi 0, that we saw directly before, now it comes from a group theoretic property, because what we are doing is, so WC is an element of G. So, but what happens when I have some G tilde that belongs to G, and I multiply it by the sum over all the elements of the group? Well, I get again the sum over all the elements of the group. The sum is left and right invariant. This is something that you have to keep in mind because it has to do with averages, right? The average is invariant under the action of group elements. We will use it later, many times. So this is the ground state. It's a soup of closed loops. And the excited states are this soup on top of which there is a pair of excitations. Now notice that as a string operator, if I have an open string and I add to it a closed string in this way, what I do is that this part cancels, and I have deformed it. But I cannot change its endpoints. So you see that when we have an excited state, so psi 1, which is some open string on top of psi 0, but psi 0 is the sum over all the loops. So this becomes the sum over all the strings with the same endpoints. So that's why the string is isotopic. It's fluctuating between all these strings. So it's not one of them. But what is fixed are the endpoints. So this is what is observable. The fact that the ground state has this huge amount of fluctuations makes it a spin liquid. What do we mean? Because it's fluctuating so much we have already seen that the expectation value of sigma x or sigma z on this state is 0. But now we understand it more physically. There are so many fluctuations that this value of the magnetization is a self-averaging over all the possible values, and then it must be 0. So there cannot be any spontaneous magnetization because there are too many fluctuations. This is a spin liquid which is on top of it topologically ordered. So there are ways of making spin liquids, so with all these fluctuations, without having this topological degeneracy. And I can give you some example later if you wish. Okay. Now, we have two more things to cover. So one is the, okay, because so all of this is for the toric code, for HTC. But now we want to study something that is a phase, you know, not one point. So we have HTC plus some parameter lambda times V. And all we know is that V is a local operator. What do we mean? We mean it's the sum plus this 4. I here are some patches on the lattice. They don't need to be a single spin operator. So, okay, let me use this. And again, I will call the diameter of X is upper bounded by R. So first of all, we want to know is if this degeneracy is robust. Okay? So we have a ground state that is degenerate, and we want to see when we add this operator if the degeneracy is split. So you remember we did it for the gauge theory, this calculation. Let me briefly redo it again, because there is a small difference, although not in the calculation, just in the meaning of it. So this splitting must be, in the ground state energy, must be proportional to the expectation value, to the matrix elements between different ground states, C0i, psi 0j, of lambda to the n, this guy to the n, at the n order in perturbation theory. Right? If you remember perturbation theory, to find the splitting, you have to diagonalize the perturbation at every order in perturbation theory in the degenerate manifold. Well, but again, this can be written like psi 0, 0, the trivial one. Then we have lambda to the n. We have this guy to the n. And then we have our W, say, 1 operator. And the same argument happens above. If this guy, there is a sum. If in this sum there is never the identity, then this expectation value will be 0. Because everything that is not identity will self-average to 0. You can do it formally. We have done it already. But you can do it formally again for any type of operator. Unless it's a do-nothing operator, in which case still doesn't give me matrix elements between two different states. So, but to have the identity means that this operator must annihilate this. Not the whole operator, but this is a sum. One of the branches of the sum must annihilate this. But this can only happen if n times r is equal L. So it can only happen at the n order in perturbation theory with n equal L over R, which means that this goes like lambda to the L over R, which is e to the minus L over R, because lambda is a small number. So this is exactly the same argument we said for the gauge theory. There is a difference, though, that you see, we are not using the gauge invariance at all. So no perturbation will split this degeneracy. It can break all the symmetries of our system. It can break the translational symmetry, it can break the gauge invariance symmetry that we have in the ground state because it's emergent. But we can explicitly break it, and it will not split the degeneracy. So there is nothing as a perturbation on heaven on earth, as long as the perturbation is local, because this is what we are using, that will split this degeneracy. So that's why these topological systems are very intriguing. Because you remember our discussion on spontaneous symmetry breaking and on quantum hard drives. When we have spontaneous symmetry breaking, and we have two states in the ground state that are degenerate, and we want to make a superposition of these, well, we know that it is unstable exactly because we have a local order parameter. So because I have a local order parameter, if my environment is coupling through that observable, and we have no reason to exclude it because we cannot fine-tune the interaction with the environment, then we will have a fast tunneling between these two states, between the symmetric and the antisymmetric superposition of the two states, which will destroy the phase coherence. However, if we are in two or more dimensions, then there is a free energy barrier between these two states, and therefore we can break ergodicity in this basis. So we are trapped either in this phase or in this phase, and that's why we can have hard drive. But we can't preserve the phase relations, so we cannot have a quantum hard drive. However, now, at least at 0 temperature, so if we are in the ground state, there is no difference between the tunneling between 0 and 1 and 0 plus 1 and 0 minus 1. This ground state manifold does not see the difference. Any two orthogonal states are connected by a non-local operator, and the tunneling amplitude between these two, if it is induced by a local operator, is exponentially small. So this is very promising because it seems that we could have a live macroscopic Schrödinger cat in principle, right? Because we are not using symmetry breaking. We are not doomed by the fact that there is a local order parameter which is microscopic, so that its tunneling time must be order 1. It's not like that. However, we have not shown that in this system the free energy barrier is right. Okay, we have not shown it. In fact, in this system, the free energy barrier is not okay. So this system doesn't work. The 2D toric code. It works in 4D, though. So in 4D, it works. Whether there is a system that works like that in less than 4D is still an open question, which is an interesting open question. Okay.
Are you saying that many particle system at finite temperature for this toric code, there is some barrier between two different?
In 4D, so yeah, so this is 2D. In 2D, unfortunately, there is no energy barrier, and the reason is, so as you know, the mechanism. So we showed that the mechanism for the energy barrier in symmetry breaking or anything for a free energy barrier depends on dimensionality. So if you remember, we showed that in 1D, there cannot be any finite temperature for its transition. It can only be at the 0 temperature. Why? Because the energy penalty that you pay depends on the boundary, and the boundary doesn't depend, it's not macroscopic, right? The boundary of something that is 1D is 0 dimensional, so it doesn't scale, it's order 1. That's the essence of the argument. So here, although the whole system is in 2D, the relevant statistical mechanics is the statistical mechanics of these operators. Because it is these operators that, if they become long enough, can annihilate this and can give me tunneling. But these objects, both in X and Z basis, are both 1D. So you cannot confine them by free energy. In higher dimensions, though, if you repeat this construction, for instance, in 3 dimensions, you will have that one type of operator, say the Wx, is a membrane, and the other one is a string. So this is Z and this is X. Well, now this has a boundary that is extensive. So this may have the right statistical mechanics and be confined, which means that, again, I cannot flip between 0 and 1. But this one is deconfined, which means I can still destroy the phase relations. So if I do all this in 3D, all I get is a normal memory, which I can only decide 0 and 1. However, in 4D, both objects are membranes, and I can confine both of them below a certain critical temperature. Unfortunately, 4D it does not exist. And it does not exist in a very important way, because we are interested in macroscopic behavior, which means that for us, the only dimensions that count are the dimensions that count, those that scale with n. If we have another dimension that is compactified, that cannot scale, it's not there. So in statistical mechanics, we are in a world that is 3-dimensional, and that's it. So so this is kind of a law of nature. So this raises the question, the fact that the only system that we know that works in 4D means that it is a law of nature that we cannot have a macroscopic Schrödinger cat. So we don't know the answer to this. Okay, so since the last thing I want to show is the entanglement in this topological phase. Okay. So first of all, let's take our side 0 in the ground state manifold. So because of this, this will be a superposition with some complex coefficients of my 4 ground states. Basically, by psi ij, I am writing this w1x to the power I, w1x to the power j on my state 0 that I defined above, and I and j are either 0 or 1. Okay? So that in this way I can label all 4 of them. And we want to consider the reduced density matrix of this state to some region A. So this is our lattice. So we want to see it locally. And as a subsystem A, we choose something that is local and that is topologically trivial. Okay? Something that we could contract. So this is equal to the trace over B of psi 0, which is the trace over B of this guy okay. Well, and this is psi 0, and now I have here the 2 W's with power j 1 and 2. Let me drop the x, you know it's there. Okay, and I need to take this trace. Now remember that this psi 0, what is it? Psi 0 is 1 over the square root of the modulus of G, the sum over these group elements, G. So let me insert this here. So this means that we have 1 over G here without the square root. And now we have the sum over G, G prime in G. And we have G, G prime. Very well. Now you remember this group property here, right? I can always write my sum over G like the sum over G tilde. I can do that. Now notice that, and we know that a G tilde is something that can deform the strings. So we don't know if these W operators go through the region A or not. Imagine they go to the region A. Then I can, if I can operate with the G tilde, any G tilde that does this and gets out of the region A. And I can do it without paying any price, right? I can put a G tilde here and the G tilde prime here. This G tilde is taking out these operators from the region A. So now we know that these operators only have support in B. So what happens when we take the trace? When we take the trace, so we have 1 over G, then we have this sum. Now we have G tilde A, GA. But we already know that this does nothing on the sum. So we have GA, G prime A, and then this expectation value, that it is, apart from the G tildes that get absorbed, is 1 W1, W2, W1, W2, I, J, I prime, J prime. And we are only left with the, so we have a delta, otherwise this will go to 0, delta I prime, delta J prime. So we're left with some ij, alpha ij star alpha ij. This has become 1. And this is now there is no dependence on ij anymore. But this, by normalization, is 1. So this is just equal to, and there is still the sum over G, G prime. This is equal 1 over G, the sum over G and G prime in G of these matrix elements. You see, it does not depend on the coefficients alpha ij. So this means that all the states in the ground state manifold are locally all the same, are identically the same. So you can take this as a definition of topological order. Of course, this also implies what we have used many times, that no local operator can make you tunnel between two different states, because simply they all have the same matrix elements. Oh, so remember, this is all spins up, and then you have all your W's. They all commute, so let me put them in this way. So these are all products of sigma x operators. So there are two possibilities. Either this product happens to be the identity, which happens when I is equal to A prime and J is equal to J prime, and then we get 1. In any other case, this product must be some sigma x operator, and the expectation value of sigma x on all spins up is 0. So those that are not like that, they just don't contribute. The only ones that contribute with 1, and it is when you get the delta. Okay, so we know that they are all locally the same. This is side 0A. So side 0A. Okay. So we would like to compute psi 0a square. We will do the calculation of this in the tutorial later this afternoon. So if we compute the square, we find something like this. We do the calculation, and we find k psi 0a. With k, we will see what it is. So you see that our local density matrix is proportional to a projector. So this means that we can diagonalize it in a basis such that it has these matrix elements. But the trace must be 1, right? The trace of this must be 1. This means that we have 1 over k of these different from 0 elements. So at this point, we could compute the entropy of this reduced density matrix. Okay. I should not have written equal here. So this is it. This means that psi 0a is equal to k 0, 0, 0. Okay. So what is the Renyi entropy of a state? We did a tutorial with the Renyi entropy? Okay. So this is equal to 1 over 1 minus alpha, the log of the trace of psi 0 a to the alpha. This is 1 over 1 minus alpha log. Well, you see that this is equal to, if we take this trace, then this is equal to k alpha plus 1 for the power n. So this is equal to minus log k, independent of alpha. So all the Renyi entropies, so including the von Neumann entropy, are the same. Another way of saying this is that the entanglement spectrum is flat. If it's flat, different powers cannot give you different moments of this distribution. It is because, so okay, so let me do all the passages. Okay, so you see psi to the alpha is equal to k to the alpha minus 1 psi. Oh, you're right. It's alpha minus 1. So you see this. Psi squared is k to psi. So if I take, then I multiply by psi again, and I get another k. Very good. So we have this. So but the trace of psi is 1. So the trace of this must be equal to this guy. So there is a minus 1 here, which gives me the right. Okay, thanks. Okay, so in the tutorial, we will see what is the meaning of k. But because we have a couple of guesses, let me just say what is k. K is GA, GB over G. So this guy G is what we know, is our normalization. It's the number of elements in our group. GA and GB are those elements that only live in A and only live in B. So you see, I am taking my group of closed strings. This is A. You know that you see there are closed strings that live inside A, closed strings that live outside A, and closed strings that go through the boundary. And I'm mobbing out those that live inside. The only ones that can contribute to the entanglement are those that cross A and B. If I do something only on A or something only on B, I cannot entangle A and B. And the entanglement is the log of K2 minus 1. It's the log of G modding out to this. It's, in some sense, the paradigmatic entanglement. I have a group of transformations. I mod out all the local transformations. And the entanglement is the order of this group. Because they are the only ones who can entangle. So the entanglement is the order of that group. Why? Because why not every entanglement is like that? Because usually states are not the equal superposition of elements of the group. They don't count all the same. So it's not just the order that counts. It's their probability distribution. But here it's flat. That's fine. OK. In the tutorial, we will see that this number as a topological constraint, so that does not scale with the system. It's a constraint, and it's topological. And we call this constraint topological entropy. So the ground state of the toric code has a topological entropy, as a correction to something that scales, that has to scale. And we will see that we will ask the question that is largely still an open question, or at least to some extent. So we will face it as a research problem and see, is this property of the ground state of the toric code a property of the phase, like the degeneracy? Or if I change this constraint is destroyed. If it is a property of the phase, then we've found a way to understand what is the order parameter, what characterizes a topological phase. It's a pattern of entanglement that has a topological character. Yeah?
Why are all the Venn entropies the same? So it's
I did a calculation. Where is alpha?
But like, is it anything to do with the system that we can argue why it's the same?
Yeah, I said, you see, it's flat. This spectrum is flat. When you take powers of a spectrum, the powers tell you how they're distributed, right? Because high powers make only the highest eigenvalue survive. Small powers say, oh, everything is more the same. But if the spectrum is flat, all the powers will give you the same information. And the Renyi entropy is the sum of these powers. The sum of the powers of the eigenvalue. Yeah.
Represent the amount of entanglement between
A and B.
A and the outside? Or
Yes. Yes.
Then, like by intuition, then the string operator that is going across the boundary should contribute to the entanglement. But
Exactly. Yeah. Exactly what we're saying.
oh,
In this counting, so we are counting how much entropy we have, how many configurations we have. But so in principle, entanglement is upper bounded by the dimension of the Hilbert space, that is this guy. But we know that local transformations at A or B, we cannot change entanglement. So I mod them out. And then we get the maximum possible entanglement compatible with this. Now, if I move in the phase, now the ground state will not be an equal superposition anymore. So this formula will change. this formula is exact, but only at the toric code point. But as I said, there is a constraint that is topological. But when I move in the phase, I am making a perturbation with local operators. So we kind of have this intuition that a local perturbation, because of the Lieber-Robinson bounds, cannot change something global. And so we hope that this constraint, topological constraint that we call topological entropy, is robust. And we know it's robust from, in the toric code, we have showed it numerically and analytically for some models, for some perturbations. But in general, it's not clear yet. So today in the tutorial, we will study a certain noise model and try to see whether we can prove that topological entropy is robust under that. So I don't know yet. It's an open proof.
In this book, you introduced this proposition of different ground state.
Yeah.
Topologically distinct ground state.
Yeah. So this is the generic state in the ground state can be written as a superposition of basis elements.
Very generic state, but like yesterday, like you also mentioned that the different sector of ground states does not talk to each other. So, like, why do you all of a sudden introduce this very relative?
No, it's exactly for this. They never talk to each other. No, this is if you want mathematically, the difference between symmetry breaking and topological order is this. Whereas in symmetry breaking, there is a favored basis. There is a basis in which the states can talk to each other. Here, no basis. There is no favored basis. Locally, they all look the same. No matter what is the superposition, there is never a local operator that can distinguish two different states.
But here you also consider the superposition that the same topological state is still the physical state. Like that one.
No, this is a basis-independent statement, because this is the generic state. The fact that I've written it in a basis doesn't mean that I've chosen a basis. And the result does not depend. If the result depended on these coefficients, then I would have selected a basis. But it doesn't. I could have written it in any other basis. No? I can make any rotation. But what is a rotation? Is some combination of these W operators. Because those are the operators that act in the ground state manifold. And then everything would follow through exactly the same.
What kind of physical example corresponds to this code, the realistic system?
This is realistic. It's a toy model. It's not less realistic than the Ising model. No, so there is no material in nature that is like the toric code, but you can make it in the lab because it's local. The coupling constants are finite and all that. In fact, there are ways of doing that. There are proposals. No, we can talk about this more later, right? I need to. So it's something that you can engineer. So there is a way of writing the same Hamiltonian, but then it's much more complicated to show because it has a richer phase diagram with just two-body interactions. And now two-body, a spin system with two-body interactions and finite coupling, something that you can make in a lab with arrays of Josephson junctions and things like that. Or even on a smaller scale in optical lattice. Okay.